so much. Thanks, Edwin, for inviting me. And yeah, really excited to be here. So yeah, as I said, I'm not really in this field. I'm mostly in the robotics field, but I'm excited about that intersection between robotics and NLP. And we're actually starting to do a little bit of work in that domain. I have actually one student who published at ACL this year who's co-advised between Percy and I know like Percy's talking later. So I'm really excited about robotics and NLP and what can we do in that space. But today I'm going to talk a little bit about some of the other work we are doing in the lab, and maybe toward the end, I'll discuss what we have started doing in the space of robotics and NLP. And in general, like my research is in the space of interaction. So how do we develop robot algorithms or AI agents algorithms so they can interact with other agents, other intelligent agents or humans? And how should we go about safety, reliability, and in general, like interactions with humans? So I'd like to today spend a little bit of time thinking about learning from humans. We do quite a bit of work on interaction, but I wanted to focus this talk mostly on how in robotics we go about learning from humans' data. And I think there are a lot of like overlaps and connections with, like across fields, specifically in this topic. So if you think about the field of like NLP or vision, right, like we've seen a lot of advances in these fields, like using deep learning, and a lot of that is due to having giant data sets and big computational models. And that set of advances, we haven't really seen that in the field of robot learning. So there's a lot of excitement in this kind of like new and emerging field of robot learning, which is basically saying, well, can we do the same thing in robotics, right? Can we collect lots of data of robots interacting in the world, and based on that, be able to get a robot do interesting tasks? And we haven't really seen that yet. And part of the reason is we just don't have giant data sets for robotics. So I just want to show this quickly. So this is a project that we did in collaboration with Chelsea's group, thinking about a project in the space of robot learning. The task was, we basically just want to move one of these objects from initial image. So this is our initial image. And there's a goal configuration that we want to get at. So we want to basically like go from the initial image to the goal configuration. And the point of this project was learning an unsupervised latent space that kind of like measures progress in these images. And we wanted to take like a robot learning perspective for that, and eventually be able to kind of like do this task. And what that involved was collecting lots of data of this robot interacting in the world. And that kind of looks like this. So the robot just like overnight, like moving around in this environment, like collecting lots of data. And kind of like at the first like image of this, like you might think this is really easy, right? Just collect lots of robot data and that'll be okay. But it's actually not obvious how to even collect lots of robot data. So the thing I'm not showing here is that for every movement of the robot here, there was our undergrad club who had to like reorder the environment and randomize the environment again, because the environment just like got changed, and basically like you had to randomize the environment and reset the environment so we can keep collecting data. And that just seems pretty infeasible for Gleb to sit in the lab like overnight, like right by the robot, help him train. So the question that we have in general is, how can we do better than this? How can we be a lot more data efficient when we are trying to learn from interactions with humans or interactions of the robots in the world? So there are two main ideas that I want to talk about today. One is, how do we go about a more data efficient approach, and how do we think about bringing ideas from active learning in the space of robotics? And then the second idea is, how can we tap into many different sources of data and use these many different sources of data to learn from our interactions with humans to be a lot more data efficient, so we don't need to have like sit in the lab with the robot all night. All right, so what is the setup that we are looking at? So the setup we are looking at is something like this. So I have my robot arm, and my robot arm is maybe supposed to do a task like pick up an object. And a common paradigm that has been around over like 20 years is, let's just provide some demonstrations for how a robot should do a task like pick up an object. And then from those demonstrations, let's get the robot to basically do supervised learning and try to imitate those trajectories, those expert behaviors that are provided by a human expert here. Okay. So this is called imitation learning, right? Or learning from demonstrations. And it has been around for a long period of time. And the idea is that, well, the robot is trying to optimize some reward function or do reinforcement learning with some reward function. And it doesn't really know what that reward is. What is the reward of picking up the cup? But by providing demonstrations, human has some sort of reward function in their head of picking up an object in a way that is safe and comfortable. And by providing demonstrations, the robot ends up building an estimate of humans' preferences here, humans' preferences of picking up an object. Okay. And as I was saying, like a lot of prior work, what they do is they think about collecting demonstrations in this space and trying to imitate that. So let's see how that works in practice. So let's say that I have my robot arm here, and I have a really simple task. I want to get the robot arm reach the goal, reach this region here. At the same time, I don't want it to hit the obstacle. And I want to keep the arm low because I don't want to like go and hit various things. So maybe I want to keep the arm low. And what I can do is I can bring an expert. This is Andy, my graduate student. And what Andy is doing is he's trying to teleoperate the robot, provide this expert demonstration, and get the robot to do that task. And one thing that I want you guys to notice is that like even Andy, who has a lot of experience in this task, he has such a hard time like achieving like this task. Like the arm doesn't even reach the goal, which is kind of frustrating. And part of the reason here is that just teleoperating these robots is pretty difficult. These are like high degree freedom robots, 7 degrees of freedom. And just teleoperating these robots can be pretty challenging. But regardless, we said, well, Andy's an expert. Let's just collect the data. Let's try to learn from that data. And the particular approach, which is commonly used in the field, is that this, if you were to learn a reward function, like one of the common approaches is this idea of maximum entropy inverse reinforcement learning, where you're saying, well, actions of humans are probabilistic. And what I'm assuming is that probability of actions of humans, AHs, is proportional to exponential of a reward function. And all I'm trying to do is I'm trying to find that reward function. So I collect lots of demonstrations. That gives me this side of the equation. And then from that, I'd like to recover what the reward function is. And what this means is if I have an action that takes me to a better state, I'm going to weight that action exponentially higher. So that's basically what this equation is saying. Okay. All right, so we can do that and we can recover a reward function. And then basically we can say the policy of my robot or the actions, the optimal actions of my robot should be the optimizer of that reward function. And in this case, you're assuming some sort of structure for this reward function, but you can imagine that the reward function should be more complex than a simple linear function of a set of features. But for the moment, let's assume that the reward function is just a linear function of a set of features that I can write like distance to the boundaries of the world and things of those form. And then I just need to learn the parameters of the reward function, the W's. Okay. All right, so let's see how this policy looks like in practice. So this is a policy that is learned from demonstrations. And then we are in the new scenario. The new scenario is you move the obstacle to the left. We have a Pringles box. So that is the object that we should reach. We should reach the top of the Pringles box. And it's like a slightly different scenario, but it's also fairly similar to what we have seen. And what we would like to do is we would like to optimize that reward function that we have just learned about keeping the arm low and not hitting the obstacle and also reaching the Pringles box. And this is how the policy looks like. So it kind of like starts off okay. And at some point the robot sees the obstacle and it's like, oh my God, there's an obstacle there. Let me try to like stay away from it. And because of that, it ends up in this like weird configuration that it can't get out of and it doesn't even like reach the Pringles box. So this wasn't so great. And really like what's happening here is because we are in such a limited data regime, robot like overfits to this kind of like obstacle avoidance element and thinks obstacles are so bad. And it's not really able to reach the Pringles box because it doesn't really like balance. It's not able to balance the two objectives that it has here. And this is like a real problem. Like this is a problem for like autonomous cars today, trying to like think about the balance between like safety and efficiency and comfort, right? Like if you sit in autonomous cars, like a lot of times they tend to be very safe, but they don't really like know how to balance that safety, but let's say comfort. And a lot of times you might feel really nauseous coming out of an autonomous car because it keeps braking and it doesn't really like balance the objectives, right? So this is in general a reward design problem, like knowing what are the preferences of humans, what is a reward function that the human really wants can be a challenging problem. And it turns out that imitation learning is one approach to go about that, but it feels like that one approach is also not really solving the problem. So at some point we thought, okay, maybe it is Andy. Like maybe Andy just doesn't know how to provide demonstrations. So we decided to bring in like a bunch of other users and we asked them to provide demonstrations, and we kind of like had the same result. And here are actually some of the things that our users said. Like they said things of the form of like, I found it hard to control the robot, and I found it difficult as someone who is not kinetically gifted. And I found that interesting because I'm personally also not like very kinetically gifted. Like I have a hard time like playing video games and things of those form. And if you're thinking about these robots like interacting with people, learning from people, we can't really expect our users to like be perfect in providing these demonstrations. And you're going to end up in these scenarios that I showed. So the question is, okay, what can we do? So I just showed you a problem here, but what can we do? Like, how can we go forward? And kind of like the gist of this is that demonstrations, expert demonstrations, they're only one source of data. And the field has been using this one source of data over and over and over again. And they've been trying to think about ways of collecting that data, but it feels like it is not enough. So the approach we've been thinking about is, could we tap into different sources of data, and could we use these different sources of data and even the multimodality of that in order to learn these preferences of humans? And then also another angle of this is maybe we should also be smarter about how we are collecting that data, right? Like collecting lots of expert demonstrations alone doesn't feel like the right thing, right? Like if it is just like around, like if it is just repeating the same sort of behavior. Like again, in the case of driving, right? Like one of my pet peeves is actually like car companies come out and say, well, my car is safe because it has been driven so many number of miles. But that doesn't mean anything, right? Like if it has been driving the same like 10 miles, like on the same highway over and over, it's not going to see informative data. And the informativeness of the data, the diversity of data is really the thing that matters. So maybe we can be smarter about how we collect that data. So those are kind of like the two core points that I'd like to talk about today. So what can we do about actively collecting data? And how can we tap into other sources of data, such as suboptimal demonstrations instead of expert demonstrations, maybe language instructions or narrations, like maybe that they can provide information, or even like pairwise comparisons. So like a robot showing you two different trajectories and asking you to rank them or compare them, or ordinal data. And also another angle, which is pretty interesting, and maybe it is like robotics related, is physical corrections. So here, like we have a robot, it does have an embodiment. It's not just an AI agent. I can actually physically move it. And based on that physical correction, the robot can try to like learn something about what humans' preferences are. Okay. So my plan for the rest of this talk is to really talk about a couple of these different sources of data. I'm going to first discuss what we have been doing in the space of pairwise comparisons and how we can actively generate these queries. And that's going to be the majority of the talk. And then toward the end, I'm going to very briefly talk about what we have been doing in terms of suboptimal demonstrations, physical corrections, and some of the new recent work that we're doing in the space of RoboNLP, thinking about looking at language instructions in an online fashion to learn from both language and demonstrations at the same time. All right, and I don't need to go over all the slides, so interrupt me at any point in time if you have any questions. I'm not monitoring chat, just like ask any questions in the middle. I'm gonna hopefully try to leave some time for questions at the end. All right, so let's talk about pairwise comparison. So what do I mean by that? So what I mean by that is I can basically show two different trajectories to a user, A and B, and then I can ask a user, which one do you prefer? And based on that response, I'm going to get some information about this underlying reward function that I was talking about. And for the moment, let's assume that that reward function is that linear nice reward that I was talking about. So I'm assuming it's a linear combination of set of features. And you might say, well, this is not realistic. Like, who does that anymore? Well, in robotics, it's actually okay. But I'll also like go back to this assumption and get rid of this assumption a little bit later. But for the moment, let's think about this reward function as a linear combination of features. So then every question, every query that I'm asking from the human generates a separating hyperplane in the space of parameters of this reward function. So imagine that this reward function is three-dimensional. So I have three parameters for the moment. So W1, W2, and W3. And then my reward function, this like the value of it is relative. So I can assume that it lies in a unit ball. So assume that the reward function, the true reward function, is somewhere in this unit ball. And I don't know where that is. That is a true preference of the human. But all I can do is I can ask a question of which trajectory do you prefer? Do you like trajectory A or trajectory B? And this question that I'm asking is generating a separating hyperplane in this space. The separating hyperplane corresponds to W dot phi equal to 0. My question is, do you like the right side or the left side? And that basically tells me if people like the right side of the hyperplane or the left side of the hyperplane. And based on the response, based on that single question, single query that I can ask, what I can do is I can reweigh my samples and I can realize that the true reward function probably lies on the right side because the human told me that they like the right side better. So this is kind of normal, like active learning in a setting of volume, in a setting where we are looking at this space of reward functions and we're trying to remove as much volume as possible from this space to converge to the true reward function. And one note is that if the human tells me that they like the right side of the hyperplane, well, I'm not going to completely remove the wrong side because humans are noisy. I can't trust whatever they tell me. So we're going to have some human update function that follows this Boltzmann rational model that humans are noisily rational. And I'm not going to fully trust like their answers like deterministically. I'm going to add a probability to my samples. All right. So then the interesting question here is that based on one question, I've got some answer, I've got some idea of how my reward function has evolved. But the interesting question I'm thinking about as a research question is, what is a sequence of most informative, diverse set of queries that I can ask from a user, right? Like what should be the next question adaptively based on my previous question? And the way we formulate this problem is as an active learning problem where we are actively synthesizing new scenarios and new queries. So the point here is that we're solving an optimization that kind of looks like this. We're trying to come up with scenarios that we're showing on the robot, trajectory A or trajectory B. And those scenarios correspond to these phis. And we want to find scenarios that maximize the minimum volume that would be removed from the hypothesis space. So what this means is if the person tells me they like A over B or B over A, in either case, like this is what the minimum is over, either case, I would be able to remove as much volume as possible from my hypothesis space so I can quickly converge to the true reward function. Okay. So this is an information theoretic objective. This is volume removal. It's actually a submodular objective, so we can use the same sort of guarantees that one gets from submodular optimization in terms of convergence of this. But there are also some elements of this that are robotic specific. So one element of this is actually a constrained optimization. And the constraint here is ensuring that these trajectories are realizable on the robot. So they satisfy things like dynamics, and you can actually run them on the real robot, like without infeasibilities. So that's what the constraint basically is ensuring. And in addition to that, we are synthesizing queries. So I want to emphasize that this is not like picking scenarios from a discrete set of scenarios. You're actually generating these scenarios from scratch from the continuous space. And that also adds quite a bit of difficulties when we are thinking about this optimization that is like a continuous optimization. Okay. And then as I was saying, well, we were using the human update function. So this is kind of like the core of the approach. And then we have done a variety of adaptations of this work where we are looking at other types of information theoretic objectives like entropy, information gain, using determinantal point processes, which are really a measure of diversity of data, and like batch versions of this. And I'm not going to go through like these different works, but if you're interested, we have a bunch of papers like in this spread of work. But this is just like the core of how you're going about it. And let's just look at a few different examples based on this. So here is a simple car simulator. It's a 2D car simulator. And we're looking at driving behavior here. And then from the left, we are looking at a setting where we don't have any preferences and the car basically the car doesn't know how to drive in this environment. So it ends up just going all over. I don't know why the video stopped. 1 second, there we go. And then after 30 questions, after 30 queries, the car learns how to keep heading. So it kind of like stays in the middle lane. Our car is the orange car. And then after 70 queries, the car learns how to drive in this space. And what that means is it learns how to change lanes and stay within its own lane and do collision avoidance and all the things that we care about. And the interesting thing that I want to emphasize here is this is 70 simple binary questions that I'm asking the user. I'm not this is like no demonstrations. And I think this is kind of surprising that we can learn how to drive in this simple driving simulator based on just 70 simple questions. And that tells us that there is quite a bit of value and potential in terms of using these pairwise preferences when we are looking at some of these domains. So, all right, so I've been talking about preferences. Preferences, they tend to be easier to collect. They tend to be more accurate. More accurate when you're asking questions like, do you want to hit a car or do you not want to hit a car? But the problem with them is that they give you one bit of information, which is if trajectory A is better than B or vice versa. Okay? On the other hand, I talked about demonstrations, and demonstrations, they're rich and informative. They give you a lot of style and movement and how fast you want to come up, like you want to do your trajectory, but they're noisy and kind of inaccurate, as we saw in Andy's trajectories early on. And in general, like this was actually the moment that we thought maybe we should combine them, right? Like I have preferences, I have demonstrations, I have other sources of data, I have language instructions, I have physical corrections, I have all these different sources of data, and each of them are really good at one thing, and sometimes they're complementary. And the question is, what is the best way of integrating them? And we actually show that if you're just looking at pairwise preferences and demonstrations, there is a way of integrating them. And the optimal way of integrating them is to actually start with demonstrations, which are rich and informative, but kind of noisy. And based on those demonstrations, basically get some prior on how this reward function should look like. And once you have kind of like an okay prior, then it's kind of it's a matter of interacting with the person in a more online fashion. And in that interaction, query the person and ask them to compare different trajectories, maybe the demonstration with two new trajectories that are generated by the robot T1 and T2. And based on the responses that you get from the human and going through this loop, update the reward function. And that is a way of fine-tuning the reward. So one way of integrating them is basically start with demonstration, like come up with like a pre-trained model based on some offline demonstrations that you have, and then in an online fashion, use the pairwise preferences to update your reward function and basically fine-tune it to specific users that you're interacting with. And using this approach, I actually want to show you how that works in this earlier example that I was talking about, reaching the Pringles box. And here on the left, this is what we have seen already. So this is just learning from demonstrations where the robot ends up in this weird configuration. But then on the right, we are looking at integrating demonstrations and preferences together. I don't know why these videos are laggy. But basically, the robot reaches the top of the Pringles box when you're integrating demonstrations and preferences. And the thing I want to emphasize here is this is, again, with very limited data. This is like 15, I think it was 5 demonstrations and 15 like pairwise queries. So it's a very limited data regime, as opposed to the thing that I was showing earlier, like in my first slide, where we're collecting data like overnight. I mean, we needed lots of data. So we can be a lot more data efficient, given that we are collecting our data more carefully and we are querying the humans in this particular. Yeah, so that's a good question. So the pairwise preferences are generated by the robot, and there are 2 trajectories that kind of look like this. This is actually something that is directly coming out of the algorithm. And at the beginning, it's like pretty messy. Like the robot is going like all over the place because it's generating it and it has like no idea like how that reward function looks like. So by solving that optimization that I was showing, this optimization, the robot, the speed corresponds to those 2 trajectories. So it comes up with 2 trajectories starting from the same initial state. And those 2 trajectories are the things that it asks the person, which one do you like? And at the beginning, it's pretty noisy, but over time, as it learns, it's going to become like more and more closer to what you would actually want to see at the end, of course. One other point I actually want to make here is something that I didn't really go over, is if you use this volume removal objective, it thinks about generating these queries from the perspective of the robot. Like, what is the most informative thing for the robot? And it could end up with trajectories that are actually pretty similar to each other. Like at the end of the day, it ends up with trajectories that could be like almost like equal. And it's really hard for the human to tell, well, is A really better or is B really better? Because the only objective that volume removal considers is what is informative for the robot. So in a follow-up work, we actually considered the uncertainty in humans' responses as well as uncertainty in robots, like robots' knowledge of the preferences. And if you consider the uncertainty in humans' responses, you end up asking easier questions from the perspective of the human. Like basically, like we optimize for distinguishability of these trajectories. And that ensures that the generated trajectories are like distinguishable and easier to compare from the human's perspective. All right, how am I doing on time? I'm not doing great on time. I'm going to skip a lot of things, but let me just very briefly mention that this type of approach that I talked about, this was the simplest form of it, where we looked at a reward function that was a linear combination of features. But as I promised, we have actually extended this to settings where we have non-linear reward functions, and there are settings where you actually need a nonlinear reward function. So this was a fun example where we're looking at a robot playing a version of mini golf, and the two trajectories are like A and B, different targets that you're trying to get at. And for this particular task, you actually need a nonlinear reward function to be able to capture all these different targets. So we represent this using a Gaussian process, and then we do active learning over the Gaussian process space. And I just want to show the comparison between our learned rewards when you're doing active learning with a linear reward, which is not able to target, like push the ball to all the targets. But if you're using the GP reward, then you're actually able to target all these rewards. And then we've actually like extended this nonlinear reward setting to more realistic settings, like when people are wearing exoskeletons. And in this setting, when you're wearing these exoskeletons, they have different gait, like people have different walking gait preferences. And what this exoskeletons can do is they can query you to see what your gait preferences are. And we have actually like thought about like using active learning in this space and actively querying people to figure out those gait preferences. The interesting element in this work is that you're actually interacting with a person and you're like probing them. So there is quite a bit of safety and comfort measures that go in here. So the active learning can't just randomly query you. You should actually think about like a safety and comfort region and query you within that region. All right. Okay, so that was kind of like my overview of what we have been doing in pairwise comparisons. But moving forward, we've started looking at some of these other sources of data. And I'm going to, given that I don't have too much time, so I think I was supposed to end at 8, I'm just going to talk a little bit about the language data. But very briefly, we have done work on the space of learning from suboptimal demonstrations. This is some ongoing work where we're looking at like a mixture of demonstrations, including optimal and some number of suboptimal ones. And the idea is, could we basically come up with some confidence measure that tells us that some of the data that we have is suboptimal, and basically reweight the demonstrations and use an off-the-shelf imitation learning technique based on the reweighted demonstrations now that we have these optimality or confidence weights. And we show that basically our approach is able to have like highest expected return compared to a bunch of other techniques that try to learn from suboptimal demonstrations. Yeah. So that was kind of like this quick, like very brief thinking about suboptimal demonstrations. Other sources of data that are pretty interesting, I think, again, like for robotics, it's pretty interesting to look at it, is physical corrections. So if you're physically moving a robot arm, the sequence of corrections that you're providing could actually be pretty informative. So here's an example where you have 2 robot arms and that are helping you unpack a grocery bag. And the robot thinks that it should put the bag on the right side, but the human has some underlying preference that maybe the right side is like there's water there, and the human really wants the robot to put the bag on the left. But what they do is they have to provide corrections on this original trajectory that the robot is providing. And those corrections are not going to capture everything at the same time because there are 2 robots here, and the human should provide basically a sequence of corrections to get the robot eventually achieve the task, while satisfying other constraints, like maybe not stretching the bag too much or squeezing the bag too much, or like not hitting like other obstacles like the Stanford had here. So what we are looking at is how can we look at these force feedback and how should we propagate those force feedback to new trajectories and then estimate the true reward function that the human has. So if you're interested in the details of this work, I can talk about it offline, but I'm going to skip that and just end the talk on the last bit, which is on the language instruction side of things. I don't know if instructions is the right word, language data. So, all right. So more recently, we have been thinking about this other source of data, language. And I was actually pretty skeptical of language because like most work, not most work, but a lot of work that I've seen in this space end up being very toyish. So they look at like very toy examples where like language is doing something and you assume so much about the robot and the robotics part being solved. And as you saw, the robotics part is not solved at all. Like doing basic things on the robotics side is pretty difficult. And what we wanted to do was we didn't want to make extreme assumptions about language or robotics. And that brought us to this new and interesting domain of assistive teleoperation. So instead of looking at a setting where you're providing like language instructions and you assume that the robot autonomously will be able to do the task, what we're interested in was a setting where there is kind of like a level of shared autonomy. There is a person still controlling the robot. There's a person teleoperating the robot using a joystick. But even that is hard, right? Like if you remember like Andy's videos earlier, Andy was having a hard time like controlling the robot. So the idea is, could we then in this setting, could we use language and like the input that the human is providing to enable better achievement of various tasks? And there's really a market for this. So there are people who use these robot arms in their everyday lives, like people like with disabilities, and they use these arms for various types of tasks, like feeding themselves or bathing themselves or putting clothes on. And it's extremely difficult to control the robots, right? I showed you Andy's videos. Here's a video of also this user who's using a robot arm to get various stuff out of the fridge. And it's very difficult. Like the thing he does is he pushes the side of the joystick. And by doing that, he's basically changing the mode of your control. You're controlling 6 things here, X, Y, Z, and yaw control of the robot. And that can be pretty frustrating when you're looking at these everyday tasks. So what we have been looking at is integrating an existing work that is in our lab, which tries to bring down the dimensionality of control space to a lower dimension and integrate that with language in order to better do these types of tasks. So the setup, the dimensionality reduction setup that we are looking at is we're looking at expert data. This is Dylan, and Dylan is basically providing these expert data of moving around the robot in this workspace. And that gives me states and actions and beliefs of where the object is going. And based on these demonstrations, we are basically training an autoencoder. We are basically training an autoencoder where we are doing dimensionality reduction over the actions. Because remember, the person is controlling 6 degrees of freedom, but what we are trying to do is we're trying to bring down the dimensionality to only 2 degrees of freedom, moving the joystick right and left and up and down. And the idea is, can we train an autoencoder so we get a 2-degree freedom that is much easier to basically use to control the robot arm. My PowerPoint is acting funny. I'm trying to go to the next slide, but it's not. This is kind of sad. Let me escape. Oh my God, no, don't crash on me. Oh, there we go. Okay, yeah. So basically at the end of the day, we're training this autoencoder, and what we're doing dimensionality reduction over is actions as opposed to states. And that gives us a low degree freedom control space that we can use to get the robot move around in this space. So that alone, that latent action alone is pretty powerful. And it allows us to basically do various types of tasks in homes. But the problem with that is there could be disambiguations in this space that 2 degrees of freedom might not be enough for doing more complex tasks where there is some level of disambiguation. And what we're doing is we're trying to integrate language along this approach. And by using language, we can basically provide language instructions along with latent actions, and together we are able to basically achieve this task. So my PowerPoint is acting funny. So maybe I'm gonna stop here and just I can maybe take any questions. I can't even escape out of this window. This is very sad. Yeah, so let me just stop here. Let me just summarize. Maybe I'll stop sharing and I'll summarize. So the quick summary here is that in robotics, data is a big challenge, right? Like you have a hard time like collecting data, and there is quite a bit of effort in trying to use like offline data sets, but it seems like pretty difficult. And multimodality plays a huge role here. So okay, so maybe I even have like large offline data sets, but maybe I can use the multimodality of that data along with all these other things that exist, like language, videos, physical corrections. And some of the work that I showed here is tapping into these different sources of data. And in addition to that, maybe being more efficient and active in how we collect our data. And I think that can really like push us closer. And robotics and language can play a huge role there. Yeah, so uncertainty like plays a huge role here. So like the first part that you mentioned is just uncertainty in the preferences, right? So that's the thing that we want to learn. We have uncertainty about what are humans' preferences when they're picking up an object, when they want their autonomous cars to drive. And figuring out those preferences is really like our goal. And of course, like we have uncertainty on that, and we can start with some priors and just try to like reduce that uncertainty using these different sources of data. But there is also uncertainty in like the data that humans are providing. And I think that's kind of like the part that you were getting at, right? Like if you're looking at like these pairwise preferences, there is uncertainty. And like there is also quite a bit of work that talks about stated preferences are different from actual preferences. Like people might say they like ice cream better than, I don't know, like mint ice cream better than chocolate ice cream. But when they're in the moment, they might actually have very different preferences. So I think that's also a very interesting angle of it. So the type of models that we are using in this space are mostly these like Boltzmann rational type of models where they say humans are not like fully rational, they're bounded rational. So they're approximately optimizing, they probably are approximately optimizing some sort of objective. And under that model of uncertainty, we are only like so much trusting the human input. And that exact model has been like used basically throughout the works that I talked about, from demonstrations, pairwise comparisons, even physical feedback. Like we don't like completely assume that, oh, if the person like pushed the arm this way, like they actually like meant it. So we add kind of like this uncertainty model. It's a good question to ask if that is a good assumption. In a lot of like functional tasks, I feel like it is, like based on the outcome that we're seeing. But if you're looking at like near the end of the risk spectrum, if you're looking at driving in near accident scenarios, I don't think this model of uncertainty really captures everything. And I think that area is like pretty interesting to look at. So when we are near the end of the risk spectrum, how should our model of human uncertainty change and how should we adapt it? Yeah, so for example, like if you like we have some work around learning how humans' preferences in near accident driving scenarios. Let's say you're making an unprotected left turn and there's a car coming like in front and like the light is turning red. Like under that scenario, like if you collect humans' data, it's like all over the place. You can't like if you collect like human demonstrations, you can't assume human demonstrations were provided by a Boltzmann rational model. So you're looking at bringing ideas from like prospect theory in that space. So like behavioral economics and prospect theory, and think about that these are like high risk scenarios and humans are just like not acting like fully rationally in these settings. So we can't fully like trust their inputs. We haven't done anything in that space. There is a little bit of work in that domain. The problem is it doesn't scale up. So I think scale has been huge. Like how to get data from humans and how to bring humans in the learning loop has been pretty difficult. And I think in general, like we need to find better ways of bringing them in the loop. Yeah, of course, like if you provide explanations, like they can be pretty informative, especially if you have the features and you can provide explanations about the features of I like this better than this because of this particular feature. That can get us like closer, but that assumes that we have a fixed set of features and like we can query people like for there is also an angle of that too. Yeah. So when they provide, even like when they provide physical feedback, right? Like you get a physical feedback, you can assume that the hypothesis space of the reward for the human and the robot is the same and interpret that. or it could be that your model, your hypothesis space is just like wrong. Maybe you don't have the right features, and like maybe the human cares about the coffee mug that is there, and that's just not modeled in your reward function. And like how to expand your reward function to model those extra elements is also pretty interesting. That's interesting. Yeah, I'd love to know like how it is different and all that. Because that's my notion of like data. We do consider outliers at times, but they're easier to like filter out. So we do filter out outliers. For example, in the work that I very briefly talked about learning from suboptimal demonstrations. Like in those cases, like one could even like have outliers in your demonstrations or adversarial data. And yeah, we have like ways of like getting rid of them, but like the focus of that work was mainly, okay, I don't have outliers, I just have suboptimal ways of doing things, and how do I learn a confidence over those demonstrations. But like there are also adversarial angles of the problem where you have like a data set that's majority like now like outliers and adversaries, and there are like really like interesting angles there too, that there's work there. We don't really like work on that. Yeah, but like in the more realistic settings, there are easier ways of like getting rid of outliers. Like we're mostly interested in the suboptimality that we get from like humans. Yeah, so that part went quick, and then my slides were not working. So I think that part was a little bit quick. So the robot arm has 7 degrees of freedom. So each joint has 7 degrees of freedom. One way of controlling them is to actually control those 7 degrees of freedom, or control the end effector, which has like these 6 degrees of freedom of yaw pitch roll and the XYZ of the end effector. So the user is actually controlling those 6 degrees of freedom. That's why it takes forever to move it around, because you have to switch between moving XYZ or controlling like angles, basically. So what we did was we tried to bring that 6 degrees of freedom or 7 degrees of freedom to 2 degrees of freedom instead, where you have a joystick, and your joystick, push your joystick up and down and left and right, and up and down and left and right allows you to do the task. And the way we are training this at autoencoder is we're conditioning it on the state. We are conditioning it on the task. The reason you're able to do that thing in general is if you know that you're like feeding yourself and you're taking like this motion of feeding yourself, maybe you can have like a 2 degree freedom that allows you to do that. So that's kind of like the key idea of it. Of course, if you want to go from any point in the space to any other point, you do need 7 degrees of freedom, 6 degrees of freedom. Like there is a reason they exist. But like the idea is like if you're doing the same task over and over, there could exist a lower degree freedom, maybe a 2 degree freedom controller. The point that language brings is maybe you're like picking up like apple and picking up a banana at the same time, and you end up with points that 2 degrees of freedom are not enough, and maybe language can do that disambiguation. So we feed in language data to our autoencoder as well. I don't know real quick. Yeah, your question was about interpretability of those 2 degrees of freedom. Yes. So they're kind of like not actually that interpretable, because there are 2 degrees of freedom that by magic are like doing the task for you. And actually, we did user studies with this, and our users did not like it at all. Like part of the reason is they feel like they're not in control. They feel like, okay, the robot like magically did it. So on every like quantitative metric, it was doing better. It was faster. It was easier to use, like all of that. But users didn't like it because they felt like they're not in control, and they felt like they are not, like they don't understand like what the 2 degrees of freedom are doing, which was pretty interesting, I think.